Hello there, my name is Avyan Atre, and this is my ISM final product for the original work. So this here is the 3D model of my rocket. As you can see, it is fully modeled, including the nose cone, the fuselage, the rail tube or the supporting tube, multiple names for this. It's basically just a straw on the side that helps the rocket stay on its launching tube. And then we have 3 fins at the bottom. Each one of these fins is in fact beveled to the exact specification. As you can see, it's a rounded edge here. You can see a little bit better if you go up to the top here. And then, in fact, both ends of this are beveled. So you have the top face, this round face here on the side, and the bottom face here is beveled too. So it is a fully beveled model of each of these fins. Then at the bottom, I also modeled the engine block here, which extends inwards, and the total engine motor itself, or the motor piece, to the exact specifications of a real-life B4-2 motor. Sorry. Okay, so that about concludes this version of the 3D model. If I run over to the rendering suite, where I produced my render of this model in a real-life environment, you can see it's in a 3D environment over here, and you can see the model is in fact resting on the floor, no clipping. All right, and then you can see how the model interacts with the physical world, and this is to scale. All right, and then we're going to pull up the Open Rocket files. So the file on the left is the original Big Bertha. How'd you say? This is my reference on the left, which is the Estes Big Bertha, a model rocket that you can go out and buy yourself. Excuse me. And on the right is the custom design that I nicknamed the Starscream. And so, as you can see on the bottom left here, you can see the flight configuration is the same, which is just the name of the motor. And then the diameter, the maximum diameter, is the exact same, considering they use the exact same body tube. These both use the standard body tube that comes with the Big Bertha, because my model is simply a reshaping of the front, which is this nose cone, and then the reshaping of the rear wings, or the trapezoidal fins, if you want to call them that. So these are custom fins for the Big Bertha, and these are the actual trapezoidal fins that I choose to use, which I got from my own math and my own calculation of essentially trial and error. I put it in the software, I did a simulation, and this is the most efficient shape I could derive from doing that process multiple times. And so I ran this software multiple times, the simulations, I believe 6 times for my own model. And then I hit compile, and it compiled all of my simulations into a single row. So you can see velocity coming off the rod, the apogee, velocity at descent, optimum delay. So the optimum delay is essentially how long you're going to set the delay for the charge to blow. Meaning, when you launch your rocket, it goes, and then to set the delay is how long the rocket motor will shoot for. Weight, the delay is the weight, and then it'll blow the charge to basically pop off the top and release the parachute. So the maximum velocity, and then maximum acceleration, time to apogee, so you can see the delay is similar, yet not the same, because the apogee is the max height it'll achieve based off of the rocket thrust, and then the total flight time will be 40.3 seconds, roughly, and then ground hit velocity. So it gives you all parts of the flight simulation. Same thing for over here. You can see ground hit velocity is actually lower in my custom model, which means it is slower on descent, essentially meaning it is a safer rocket and less likely to break because it is moving slower. Furthermore, the flight time is also much longer, meaning it's traveling much higher, and it's doing so a lot more efficiently. Time to apogee is also a little bit lower, meaning it's accelerating up to that max height. And then across the board, the apogee, the max velocity, and the acceleration are all higher on my custom model, meaning it is a pretty sweeping success. All right, and so the only real difference between the two is, as I said before, the nose cone and the fins. However, I did also change the composition of this engine block, this tube coupler. Initially, I believe it was made out of paper. However, I traded that paper engine block for a balsa wood engine block, which it was a simple choice. Essentially, balsa wood is widely available at any hobby store, and using balsa wood it helps manage the center of pressure. As you can see this over here, this red dot is the center of gravity, and the checkerboard blue and white dot is the center of pressure. The closer these are together, the more stable this tends to be. And so my rocket is a lot more stable. As you can see over here, stability is 2.58 I forget the calibers. 2.58 calibers versus 0.836 calibers. So this is much less likely to tumble during flight. You can see my top speed is higher, significantly, and my maximum acceleration is also much higher here. Furthermore, the apogee is nearly doubled, going from 66.5 meters to 102 meters maximum height. So a pretty sweeping success for my custom model. Thank you.